Machine Chillers Incorporated has developed a new cooling system based on vortex tubes that uses air as a working fluid. Bedell Incorporated has been contracted to provide an independent review of the system and determine its capabilities. This will be accomplished by characterizing key relationships for the vortex tube system, specifically between the input pressure, P3, and the cold temperature output, T4C, the input pressure, P3, and the cold mass flow rate, M.C, P3 and the hot temperature output T4H, and P3 and the hot mass output M.H. Additionally, the compressor's ability to pressurize the system will be characterized through determining the motor speed and P3 pressure relationship. Also, the heat and energy transfer at the load will be calculated to determine the system's capabilities. The system's experimental setup is shown in Figure 3 with the pressure regulator and accumulator tank. In Figure 4 has a slightly different system layout using the motor and compressor. As shown in Figure 3, the system consists of pressure sensors to measure the pressure at P3, P4C, P5, which is the pressure after the load. The flow sensors in green are used to determine flow for cold and hot air. The vortex tube is used to separate hot and cold uncompressed fluids, as temperature readings will be taken for the hot and cold side of the tube, T4C for the cold side and T4H for the hot side. Also, temperature sensors will be used to determine the ambient temperature, the temperature after load, which is T5, the temperature before and after the heat exchanger, which are T1 and T3 respectively. There is also an aluminum block insulated with styrofoam to serve as the system's load. There is a pressure regulator to input shop air into the system. The motor and compressor are used to draw air in at a low pressure and then discharge the air at a higher temperature and a higher pressure. The data collection will be run for temperature, pressure, and mass, flow rate, and motor RPM at various nominal PSI for the system with tank and system with motor and air compressor in order to characterize and model the steady state relationship between P3 and T4C, mass flow rate cold, T4H, and the mass flow rate hot. These values are used in order to calculate Q air, Q ambient, and Q error for the system. Also, uncertainty analysis for the Q air, Q ambient will be conducted based on instrumental uncertainty precision and accuracy and error propagation analysis to determine the system's capabilities. The system model has the assumptions that the lumped mass model can represent energy change over time, the volumetric flow rate is not scaled to standard temperature and pressure, that the temperature outside of insulation is at ambient temperature, that the heat transfer from ambient heating is slow, that all constants, conversion equations, and initial measurements have negligible uncertainty, and that the pressure drop across flow meters is negligible.
With the experimental model finally set up, it was now time to collect data. 4 different stations throughout the experimental setup were monitored for their temperature at various times and for various pressure inputs. The stations monitored were all after the air had passed through the vortex tube and were heated and cooled. One side was obviously cooled and the other side was heated. The resulting temperature responses can be seen at the top right of the page, and they follow this trend. Each station's temperature was recorded until a somewhat steady state could be observed. Once this happened, the steady state temperature was then recorded and the pressure was raised in the system. This resulted in a change in the steady state temperature of each station. Each steady state temperature and pressure relationship were recorded and fit with the linear regression model. Here we can see the steady state temperature response in respect to pressure of the hot side of the vortex tube. As we expect, the temperature increases in respect to pressure as it is pushing more hot air through the system overall. This is the temperature response of the cold side of the vortex tube. As one can see, the points do not seem to represent a linear model very well, and thus our linear regression does not look like it models the data well. However, we do see the relationship that when pressure is increased, the temperature falls, which makes sense as more air is being pushed through the vortex tube and thus being cooled. Here we see the temperature response of the cold air after it's gone through the load. This temperature is obviously a little warmer than that when it's before the load, as it has absorbed some heat from the load in order to cool it. This follows the same trend, however, as more pressure means more cool air is being pushed through the system. Lastly, we have the temperature response of the load itself. It's going to follow the same pattern as when pressure increases, the steady state temperature of the load decreases. This is because more cool air is being pushed through again. However, this also tells us that our system's actually working, as the purpose of the system is to actually cool the load.
The top left figure displays the motor and compressor, with the figure on the right detailing a schematic for the system and how air is driven in at low pressure and then pushed out at a higher temperature and higher pressure. The relationship between the motor and the compressor system was determined through running the system at different RPM and collecting data for pressure at P3, the input for the vortex tube. The experimental data is shown in the bottom left figure for the motor speed versus P3 at steady state. The figure shows that at 0 RPM, the measured pressure was 0 and then rises to 145,870 newtons per meter squared at 366.69 RPM, and then again rises to 289,762 newton per meter squared at 779.28 RPM. The average P3 was taken each RPM value and run through a York regression to determine the steady state relationship between the two. The bottom right figure is a plot of the 3 experimental data points for motor speed versus P3 and the resulting linear regression. The fit for the data is linear, so as motor speed increases, the P3 increases in a linear fashion.
To see where discrepancies come from in our system, we look at the heat exchanger and the accumulator. These two elements will most likely cause a little bit of discrepancy in heat transfer throughout our system. 2 different pressures were tested and their temperature responses at stations 1 and 3 were recorded to see what the change in enthalpy that occurred between the two. 2 situations were taken, assuming that the 0 psi situation yielded 0 change in enthalpy. However, when 20 psi was injected into the system, between the stations 1 and 2, it was found that there was a loss of 6.69 joules of enthalpy. And then when 40 psi was injected, the change in enthalpy was found to be negative 25.05 joules. This makes sense due to the fact that when we push more air into the system, we expect that there would be more heat transfer or enthalpy change to occur. On the top right, an attempt at modeling the enthalpy in respect to pressure was done. However, there's only 3 data points, and thus we need more information in order to truly try to get a relationship between the two.
The next step of our analysis was to conduct a steady-state analysis of an insulated refrigerated load in order to determine the ambient heating through insulation at each nominal PSI test. The load, an aluminum block as seen in the picture to the right, was insulated with styrofoam. To do this analysis, the experimental and theoretical thermal conductivities were calculated and compared with one another. Using the thermal conductivity, area and thickness of the styrofoam, and the relationship displayed in the formula, the theoretical value of the thermal resistance was calculated. It's important to note that the experimental thermal resistance value was calculated under the assumption that the system was at steady state, which means that the Q dot air is equal to the Q dot ambient. These values of thermal resistances of our theory 24.86 and our experimental 2.31 were then used to calculate the thermal conductivities. The thermal conductivities were found using the energy balance at steady state as seen in the formula displayed. The experimental thermal conductivity was calculated to be 0.3538 joules per second meter Kelvin, while the theoretical was 0.033 joules per second meter Kelvin, indicating that there is a very large discrepancy between the two values of order of magnitude 10. The next step in our experimental analysis includes modeling a transient cooling of a load, meaning that it would not be modeled at steady state anymore, both at building air at 80 psi and by using a compressor at 40 psi, and the predicted energy transfer from theory will be compared with the measured experimental results from these tests to determine how much deviation there is, so the Q error will be found. The uncertainty propagation will also be done to determine the confidence of each conclusion drawn and to determine whether the sensor uncertainty or the errors of the model are causing this uncertainty. So in conclusion, we were tasked with characterizing the vortex tube input and output parameters, characterize the compressor's ability to pressurize the system, and to characterize the heat and energy transfer at the load. After analysis, we concluded that the steady state temperature response for each station was found to change in respect to the input pressure. We also found that the P3 increases linearly as the compressor motor speed increases. We also found that there was not enough data to model the loss of the heat from stations 1, which is the heat exchanger, to station 3, the accumulator. And finally, our experimental thermal conductivity tests were far from the theoretical values, since there was a factor of 10 difference between them. Thank you very much for listening.